All right, we're going to continue on here talking about chemistry, acids, bases. You noticed, and I was waiting for somebody to say, "Yeah, that sounds about right. Sounds about right over there." That's good. What if? All right, fine. Gonna, we're gonna talk about stoichiometry, some gas laws, all the good stuff. All right. All right. So we got into acids and bases. And obviously, as we talked about, we have our Bronsted-Lowry definition. Again, a acid is a proton donor. Once again, we do want to remember that again, it's not just the H plus, but the not just the H, but the plus part of it is important as it does affect the charges. Base is a proton acceptor. Again, that creates our relationships that we talked about, acid and bases on the left-hand side, our conjugate partners there, acid and conjugate base on the right-hand side. Again, acid to base and base to acid. Remember, again, it is only that one H plus difference that we talked about that makes them a pair. We had our equations, right? Our pH is equal to minus the log of the H plus concentration from our pH scale of 0 to 7 acidic, 7 to 14 they're basic, and 7 being neutral. We also had our POH is equal to minus the log of the OH minus concentration. And again, the pH plus the POH equals 14. So again, it does give you some options to use in terms of solving some of these problems. We also have obviously our original there, KW, which is our H plus concentration, our OH minus concentration equals 1 times 10 to the minus 14. Remember again that the H plus concentration and the OH minus concentration go opposites of each other. So as one goes up, the other goes down, and vice versa. We also can, if we have the pH, again, we could get the H plus concentration from that. And that's going to be the inverse log of the negative pH. And you could also get the OH minus concentration if you have the POH. And again, that's going to be your inverse log of the negative POH. So again, gives us a variety of ways that we could solve these problems. Again, no way is right or wrong per se, as long as you do it correctly. We want to again answer the question as we talked about a number of times, I think last time as well. Just one answer for the acid basic or neutral solution, not all three. Yes. And again, probably pH again is probably where you want to look because that's the scale most people have in their head, and not the POH, which again runs opposite. Any questions on that stuff? Yeah.
7.4 was the peak for one of the examples.
Yeah.
It's considered basic.
Yeah.
So it has to be exactly 7.4.
Yeah. So technically speaking, the definition of neutral is when the H plus concentration equals the OH minus concentration. And technically speaking, when that occurs with KW, the H plus concentration, or really both of them have a concentration of 1 times 10 to the minus 7, which means when you lay up the pH for that, you basically have pH of 7, which is right on the nose. So we'll roll with 7 are pretty darn close to 7, like 6.999 or something like that. Other than that, anything slightly above it, whatever you want to think about, like 7.1 or something like that or above, or a little bit below it, we'll call it slightly acidic or slightly basic in that case. But the true definition of neutral is basically when those guys equal each other, which again would get you technically a yield of a pH of 7. Yeah. Other questions? All right. So we talked about some relationships, I think, of acids and conjugate bases. And remember that a really important relationship that we talked about is the idea that if you have a strong acid or a strong base, its conjugate partner will be considered relatively weak. And basically what that means is pretty much will not continue to react and affect the pH of that solution. Some things can react with water and actually go on to affect the pH of the solution. But if it comes from a strong acid or strong base, again, it will be relatively weak in terms of its conjugate partner. Now, if you have a weak acid or a weak base, its conjugate partner will be relatively strong. And what we mean by that, again, is it's not like a strong acid or strong base as partner. It's going to be strong in the sense that we'll be able to continue to react with water and will have an overall effect on the pH of that particular solution because of its presence. It is still going to be, again, weaker than any strong acid or strong base, but again, it will have that ability to do so. As we talked about in terms of acids, there's kind of a six-pack there of acids that you should know: hydrochloric acid, nitric acid, sulfuric acid, hydrobromic acid, hydriodic acid, and bless you, and perchloric acid. This is kind of a six-pack of pretty much strong acids. And again, it'd be good to know those because pretty much if it's not one of those, you can make a pretty good assumption that's going to be a weak acid if it's not one of those. So just by kind of a process of elimination. There'll be other ways that you'll be able to kind of determine that. And that's what we see here in this table. Strong acids there, relatively weak conjugate bases on this end. And again, opposite here, kind of a weaker acid down here, a stronger conjugate base sort of on that side. Now, in terms of the bases, strong bases, pretty much your, like I said, group 1 and group 2 on the periodic table there. This guy kind of hang over there to calcium, maybe a little bit of strontium and barium. These guys with hydroxide are pretty much going to be your strong bases that you most likely come across, group 1 or group 2 on the periodic table. Now, the deal is if we have a strong acid or a strong base, when they break apart, they're going to, again, 100% break apart into ions. So, for example, if we had hydrochloric acid, and it breaks apart into basically H plus and Cl minus. In terms of the pH of this solution, it is the amount of H plus that comes into solution that's important. So you could go into your pH equation. And in the case of this, it is a 1-to-1 relationship, which means pretty much whatever the concentration of the acid is will also be the concentration of the H plus that's in that solution. And you basically go in there. Now, a base is a little bit different, not too much different, other than if you had something like sodium hydroxide, when that breaks apart, you get a little Na plus and OH minus. And once again, this is going to be 100% ions, just like it is over here. In this case, we don't have H plus because it is a base, but we do have OH minus. And from that, we can actually get our POH. And again, same idea here. Whatever the concentration of this guy is a 1-to-1 relationship in this case. That will be our hydroxide concentration. And then you can use something like the pH is 14 minus the POH to get to the pH. So if you have a strong acid or strong base sort of given to you, which sometimes happens, not just the generic H plus or OH minus concentration, what you need to do is basically figure out what is the concentration of the H plus and are the OH minus, and put it into the appropriate pH or POH equation. The good news is most strong acids are monoprotic. They have one hydrogen to give, which means whatever the concentration of the acid is probably going to be the concentration of the H plus. So there's not a lot to sort of figure out there. Any questions on that there? So once you try here, we got a couple of a strong acid. Okay, so let's take a look. So first off, we want to recognize this hopefully as nitric acid, which is one of our 6 strong acids. So what we know about this is when this is in solution, pretty much it is not going to stay together. It is going to 100% break apart into H plus and a little bit of nitrate action happening there. So again, 100%, this is what we have. We have 0% of that in solution. At this point, we want really for pH, it is the H plus concentration that we need. So the concentration of the whole thing here is 2 times 10 to the minus 3 molar. It is, hopefully you remember from last semester, it is a 1-to-1 relationship between those. And that means that the concentration is 2 times 10 to the minus 3 molar. If you're not sure about that, let me do it the long way here just to remind you. That is moles per liter of nitric acid. Doing a little mole to mole relationship, just like you do in stoichiometry. See, I wasn't kidding. We'll do a little stoichiometry action. 1 mole of nitric acid, 1 mole of H plus, moles of nitric acid cancel, and gives you 2 times 10 to the minus 3 moles per liter of H plus. So 1-to-1 relationship here, same concentration. 1-to-2 relationship, multiply it by 2. 1-to-3 relationship, multiply it by 3, basically. Any questions on that there? So this is our H plus concentration, which is what we need here for our pH. So putting that in there minus the log of 2 times 10 to the minus 3. Hit all the right buttons there. Minus 3. Oh, I don't know. Going to give us a pH of 2.7 in this case. That is an acidic pH, so that probably makes sense as that's an acid, right? Obviously here, if you got like a pH of 12, probably something went wrong in this case, yeah. Question on that there. Looking at the second one, that's barium hydroxide. That is a strong base. So once again, as I said a second ago, a little lithium, a little sodium, a little potassium hanging right, calcium, strontium, and barium. Again, kind of your strong bases. So in this case, in solution, our barium hydroxide here is going to 100% brick apart into barium ions and a couple of hydroxides in this case. In this case, we do have the concentration here, 1.8 times 10 to the minus 2 molar. We actually need the hydroxide concentration. That is not going to give us our pH, but it will allow us to get to our pOH first, and then we could use that obviously to get to our pH. In this case, it is not a 1-to-1 relationship. It is a 1-to-2 relationship, which means to get the proper concentration, you need to take 2 times the concentration there, 1.8 times 10 to the minus 2. Or you could do the longer stoichiometry part of calculation if you like, but it should come out the same. Get you 0.036 molar as our hydroxide concentration. That means in our pOH, negative log of the hydroxide, negative log 0.036 there, and minus the log of that. That's going to give me a 1.44. So at this point, in case you were confused, that and you thought that was the pH, that should not make sense to you either, because that would then be an acidic pH, and this is a base, right? So this again is the pOH. So we do need to go one more step here. So a little pH is equal to 14 minus our pOH. Going to get us 14 minus 1.44. And that's going to give us a pH we could be proud of 12.56, which is basic in this case. And that does make sense in this case. So again, I would say probably in this situation, it's going to be more the base you might have to adjust than the acids, since most of the acids are monoprotic and just have one hydrogen to give. But not all bases you'll have to adjust, but you just gotta make sure you get the right concentration. So if you have a strong acid, you just need to get the H plus concentration from it. Got a strong base, you need to get the correct hydroxide concentration from it. So you can get the pOH and then obviously subtract 14 there and get your pH from it. Questions on strong acids or strong bases, how to get the pH. Okay. All right. In case you missed it, here's a list of some more strong acids and strong bases, which are the same ones we've been talking about. All right, so what happens with weak acids and ultimately weak bases? They are different, and a little bit more work needs to be done when you're trying to calculate the pH of a weak acid or a weak base. A weak acid or a weak base is a weak electrolyte, which means it will mainly stay together, but will produce a little bit of H plus or OH minus in solution, which is why it is considered a acid or a base. Bless you. So if we have just a generic acid here, that's what the HA is here, just a nice weak acid in this case. By the way, you could just use that for an acid as well. We could show the dissociation here of this acid into H plus and A minus. It is a reversible reaction, which means it will set up our favorite thing ever, equilibrium. And we can write an equilibrium constant for this, just like we did previously. Products over reactants. It's for an acid, so I'm going to go with that's what the A means there. So Ka would be the equilibrium constant for a weak acid. The Ka, as it increases, or as the Ka value gets larger, the strength of the weak acid actually increases as well. Why would that be? If I have a large K value, that means when I reach equilibrium, what do I mainly have? Reactants or products? I mainly have what? Products, right? So if we have a larger Ka value, that means when we reach equilibrium, we mainly have products. And because we mainly have products, that means we have a lot more free H plus floating around. And that's pretty much your definition of an acid, right? Is the ability to produce H plus in solution. So the larger the Ka value, the stronger the weak acid will be because it will be able to produce more free H plus in solution than a weak acid that has a smaller Ka value. Yeah. We should also remember that it is still nowhere near as strong of an acid as a true strong acid is. So it's still a weak acid. So what we're comparing there at the bottom is between two weak acids, which one would be a stronger weak acid? Yeah. Any questions on that? Do we have Ka values for strong acids? The answer is no. You typically do not have a Ka for a strong acid. And that is because a strong acid is a one-way street, right? So if you had something like HCl, it is 100% going to break apart into ions. None of that. Nobody's going back in the other direction, which means it's not going to set up an equilibrium. And since it doesn't set up an equilibrium, there is no equilibrium constant for it. So how do you know if you're dealing with a weak acid? Got a Ka value, that's a pretty strong indication that that acid is a weak acid. It's not one of those six we talked about. It's probably a weak acid you'll find in that table. If you find a strong acid in a Ka table, probably the only one that you'll find maybe is sulfuric acid. And it will usually say in that table the Ka value is really large, which doesn't do much good in terms of calculation or anything like that. So in general, we do not see Ka values for strong acids because they do not set up an equilibrium. They are only for weak acids, which again tells you you're dealing with a weak acid in that situation. It also tells you, adding to our big list of K values now, we have Kw, Ka now, we got Kp, Kc. We will need to solve these guys a little bit differently than a strong acid or strong base. We will need to use a ice table here, just like we did in equilibrium, basically to solve it. The good news is pretty much we do an ice table and we're interested in the value of H plus in this case. The additional thing that we do is we typically will then go into the pH equation and get the actual pH of it. So that's a slight difference of what we do here. So here's a table. You have a similar one in your book of some acids. Again, some acids are monoprotic, some are diprotic, and some are triprotic. And just a reminder that if an acid is monoprotic, this is kind of the generic formula that's used for a monoprotic acid. It basically means that it has one H plus that it can give away. An example of that would be something like hydrochloric acid. If you have a diprotic acid, the sort of generic formula for that is something that looks like this, H2A. The reason for that is the A actually has a -2 charge in this case. And an example of that would be like H2SO4. And you can have a triprotic acid, generic formula, sometimes use that. And you can have something where 3 of these come off, basically. And this guy actually has a -3 charge, like phosphoric acid. So monoprotic, diprotic, triprotic, you have weak acids that are all of those things. You have weak acids that are monoprotic, you have weak acids that are diprotic, and you have some that are triprotic as well. Again, as we'll talk about a little bit later on, I think in this chapter a little bit more, those hydrogens do come off again one at a time. So something like sulfuric acid will not, as this overall equation shows, drop both hydrogens at once. They actually will come off one at a time. Same thing with the phosphoric acid. It actually, again, will not drop all 3 hydrogens at once. It will come off basically in a stepwise sort of dissociation, one at a time. And we'll talk about that a little bit later on, I think, a little bit more detail. So you will sometimes again see both parts of those things, the diprotic acids and triprotic. So for example, here in this particular one, that is the first hydrogen comes off, second and third. There is, as we will see shortly, a K value that actually goes with each of them. So they actually come off one at a time. All right, so let's take a look at this here. We want to, what is the pH of a 0.5 molar hydrofluoric acid solution? The Ka value we'll use for hydrofluoric acid is 6.4 times 10 to the minus 4. Why don't you give it a go? Again, approach it like a normal equilibrium problem. Again, try to figure out what the H plus things that you want to think about when you're doing these type of problems, especially in the next few chapters, is sometimes a lot of people will overlook some information that's maybe given to you in the problem. And sometimes that could help point you in the right direction if you're not sure. And what I mean by that, for example, maybe you're not sure what type of acid that is, but I definitely see a Ka value. Or if it wasn't given to you, I could obviously go to a table perhaps and find that Ka value. And that should tell me that because it's a Ka value, it's a weak acid, right? And it's going to set up an equilibrium. That also should pretty much scream to you in this class. I should, be doing some type of ice table is probably the move that seems logical here. So to do this, we will take our acid, and again, we want to show it dissociating in our equation. I, again, typically don't include the water in my reactions here of an acid breaking apart or dissociating. If you want to include the water in your equation, it's perfectly fine. The only difference is you'll get H3O plus on the right-hand side rather than H plus. So if you want to show it like I did there, or if you want to include the water, absolutely nothing wrong with it. You will just get H3O plus and F minus. And again, H plus and H3O plus, pretty much the same thing. And that's really what we're interested in this case. So I'm going to go back to just the HF here. And really at this point, it does just sort of default back to a normal sort of equilibrium problem. The only thing given to us is the initial concentration of this guy. That also means that we know and can probably safely assume that those guys are going to be 0 in this case. That also helps us understand which way this reaction should be going in this case. And it should be heading towards the product side as we only have reactants to start with. So that should kick off the forward direction. That also should make us feel pretty confident when we get to the change part that minus should be over here and a little plus action should be on the product side, right? Now we could just bring this down. We got a 0.5 minus x, x, and x. Any questions on the ice table there? Obviously, if you did this reaction, should you be putting any numbers on the water? You should not, right? Because it's a liquid and it should not be included. So again, maybe also a benefit of not putting the water in there so you don't maybe do something you shouldn't. But again, it's not wrong to do it that way. At this point, like normal, we want to use our Ka expression in this case, which would be the concentration of H plus, the F minus concentration divided by the HF concentration, and that's going to equal our 6.4. I'm running out of room. I'll go below it, times 10 to the minus 4 there. Once again, we're just going to take our equilibrium line into here, and we're going to solve for x. That will essentially give me x squared divided by 0.5 minus x equals 6.4 times 10 to the minus 4. When I look at my k value here, it is a large value or a small value? It is small, which means why not give it a try, right? We can try our assumption in this case because we have a small value of k. If you don't want to do the assumption, you could still roll quadratic if you want to go that route. But here we're going to assume that x is equal to 0. Remember that it is not all of the x's. It is really just the x's you're going to be subtracting from a number, or you are going to add to a number, basically. So if I do that, it looks like I will end up with x squared divided by 0.5 equals 6.4 times 10 to the minus 4. I'm going to multiply this guy to the other side. After I do that, I'm then going to do a little square root action. Yeah, so multiply first and then square root. And if I do that on my calculator, we will end up with basically x squared is equal to 0.00032. Now I'm going to square root it. That is going to give me a 0.01789 as my x value in this case. Now, whenever I do the assumption, I also need to make sure that I check it to make sure it is okay to use. Remember, we are following the 5% rule. Once again, to check your assumption, you are going to take your x value. So I'll do it right here, 0.01789. You're going to divide it by what you were going to subtract it from, 0.5, times it by 100%. So hopefully we are good. Let's see. That looks like a 3.6%. And that gets a happy face. That means our check is good in this case, right? We don't have to go back and do it like the quadratic way. At that point, really in this case, we're actually interested in just the pH, right? So if we go to our table, we can see at equilibrium, the H plus concentration is actually equal to X, which means this is actually the H plus concentration. That means we could go into our pH is equal to minus the log of 0.01789. And have that number somewhere. There it is. We'll go a 1.75 in this case. Or really a 1.8 on sig figs there, since that has just one sig fig, should have one decimal place in this case. That is acidic, which does make sense. Again, we are dealing with an acid, so if you end up with, again, a basic pH at this point, something definitely went not so right there. Question on that one there. So as you can see here with a weak acid, it really is the same equilibrium calculation. The additional step you need to do is just probably throw it into the pH equation at the end there and get the pH. That is usually what you're looking for. You may be asked what the concentration of everybody is, but usually it's the pH. Any questions on that? So a reminder again that it is important to check your assumption. So for example, we had the exact same problem, but the concentration was 0.05 molar instead. And we went through our ice table like we just did. And we had initially 0.05 molar, 0, 0, change, minus x plus x plus x. 0.05 minus x, x, and x. Here we would then get x squared divided by 0.05 equals, what we're using there, where's that thing? 6.4 to the minus 4. 6.4 times 10 to the minus 4. Again, we did our assumption, obviously, in this case. That would be minus x. We're going to assume that is 0. I guess x squared 0.05 equals 6.4 times 10 to the minus 4. we're going to multiply and again divide square root like we did previously. So 6.4 to the minus 4 times 0.05, a little square root action. Going to give us an x value in this case of 0.00566. We divide this by 0.05 times it by 100%. We end up with 11.3%. That gives us an unhappy face, yes, and we could not do the assumption here. So again, just a reminder that the assumption will not always work. You should definitely check it. You might be wondering, they seem kind of like the same numbers, 0.5 molar versus 0.05 molar. One works, one does not work. The reason for that is the actual concentration, right? The 0.5 is a higher concentration than the 0.05. So when you lose a little from the higher concentration is not as big a deal as if you lose a little from the smaller concentration. I like to use the pizza example. We got a brand new pizza, take one slice out, not a big deal. Still have, pretty much a whole pizza left. You get down to, just 2 slices left in the box. Nobody wants to take them usually, right? But if you take one slice out of that deal, you just took half of it away. That's a much bigger deal, yeah? So the concentration plays a big role in terms of whether or not, for example, your assumption will work or not. Again, kind of the larger the concentration, good chance it's going to be okay. But again, if you're starting with a smaller concentration, whatever you lose is probably going to be fairly significant. Any questions on that there? All right, so as we saw here, we want to identify the major species that will affect the pH. In most cases, we can ignore the autoionization of water. So what that means is, in most cases that we do here, pretty much all cases that we do in this particular class and in most classes that you do, we do not worry about the autoionization of water, basically water itself producing H plus or OH minus. So we go under the assumption in this class and pretty much most of the time that you do the calculations that all of the H plus that's in that solution or all of the OH minus that's in that solution comes solely from the acid or base. None of it is being kind of contributed by the water by itself reacting with water. And with that in mind, we pretty much just look at the acid or base in terms of the H plus or OH minus concentration, and that allows you to get to the pH or the pOH that way. Some books and some people will say, well, the concentration of just water by itself, H plus or OH minus, can be much larger than what the acid's providing. So we should just use the water's concentration. So we're not going to do that. But in case you do see it, sometimes in books, they'll kind of talk about that. We're just going to assume that everything in terms of H plus or OH minus comes from the actual acid or base is going to be the major contributor. Now, as we saw there, we do an ice table and we do solve for X. And in the case of an acid, usually the X will pretty much equal the H plus concentration. You just need to, again, take that additional step in most cases just to put it into the pH equation and calculate what the pH is. You, again, can solve these problems the same 3 ways we solved previously equilibrium problems. If it happens to be a square root, probably not going to happen too much, but if it does, you could do that. If you could do the assumption like we just did, and again, like usual, you could always do the quadratic if you want to solve it that way as well. All right, so once you get a go there, what is the pH of a 0.122 molar monoprotic acid? Again, monoprotic, as we just talked about, you can use that as the formula if you like. All right, so let's take a look and see how you're doing on this one. Again, you could use, if you don't have a formula for a monoprotic sort of acid, something like HA. In this case, it is going to break apart into H plus and A minus. Once again, I do know it is a weak acid because I see a Ka value associated with it, which again should tell me I should probably do an ice table in this case. We could write a Ka expression, which is our H plus times our A minus divided by our HA, and obviously that equals our Ka value. Going into our table here, we'll then start initially with 0.122. 0 and 0. Again, that tells us we should be heading to the product side. So minus x plus x plus x. And that means here again at equilibrium 0.122 minus x, x, and x. Any questions on the ice table here? At this point, we're going to go into our expression, and that will get us x squared divided by 0.122 minus x is equal to 5.7 times 10 to the minus 4. You could assume that x is equal to 0, and you should check it, and you know it is a bad thing there because that's 6.8%. So hopefully you checked it, and you cannot use the assumption here as it is not good. It's bad in this case. That means that we do need to solve it quadratic way here. So we're going to multiply that to the other side, and that's going to get us x squared is equal to 0.122 times 5.7 to the minus 4. 0.00006954 minus 5.7 times 10 to the minus 4x. Going to bring everybody to the same side. So x squared plus now 5.7 times 10 to the minus 4x minus 0.00006954 equals 0. That's going to be our A, B, and C here for our quadratic. And going in, we will get x is equal to our negative b, which would be negative 5.7 times 10 to the minus 4, plus or minus, if we do what's inside the square root, 5.7 to the minus 4 squared. If I can find that button, squared. Minus 4 times a, which is 1, times c, which is negative 0.00006954. Gonna get us inside there 0.000278. We're going to then square root that. And after you square root it, 0.01669, all divided by 2 times a, which is 2 in this case. Going to give us two values here, 5.7 to the minus 4 plus, that's negative, huh? Negative 5.7 to the minus 4 plus 0.01669 divided by 2. Going to get us an x value of 0.00806 if we go the positive way. We subtract now, minus 5.7 to the minus 4 minus 0.01669 divided by 2. Going to give us a negative 0.00863. Now, clearly in this case, we are looking for our H plus, and that is equal to X. So I think negative is not going to be a good choice here. So we cannot have a negative concentration. So we'll go with the positive as our H plus concentration. That means our pH in this case, negative log of the H plus, negative log of 0.00806. 0.00806. Looks like a pH of 2.09 in this case, yeah? Question on that one there. So again, another important reminder that you should check your assumption. They will not always work, and they will work, but sometimes they will not as well. So again, if you don't want to worry about that, you could just stroll right through with the quadratic if you wanted to. But I would give the assumption a try because if it works, then obviously it saves you some time. Yeah. Yeah. That's just, yeah, it's just the rules in terms of the number of significant figures, and the concentration is how many we should have in the pH. And truthfully, what I have now really should have three decimal places instead of 2.09. So I guess it really should be 2.094 should be what we should have there. But yeah, and that would be based off obviously doing this guy here, yeah, which has 3 sig figs. Yeah, I'll pop it in there. Other questions? All right. All right, so try another one here. Calculate the H plus concentration. in a 0.01 molar solution of a little hydrocyanic acid. I think that's what that is. Ka 6.2 times 10 to the minus 10. Perhaps the right answer is up there. Always go with none of the above, right? That's choice. All right, see what you get. Okay, so let's take a look. Once again, we don't want to overlook information in the problem. So HCN, that's a Ka value, which tells me it's an acid, also tells me it's a weak acid. So once again, if you're not sure where to begin, go with the ice table, yeah? So we're going to again show this weak acid breaking apart into H plus and Cn minus. Initially here, we were given the concentration of it as 0.01. We'll have 0, 0, change minus x plus x plus x at equilibrium 0.01 minus x, x, and x. Question on the table there. Like normal, just a regular equilibrium sort of deal. We're going to go into our Ka expression, which is our products, divided by reactants. And that's going to equal 6.2 times 10 to the minus 10. Popping in our numbers there, x squared over 0.01 minus x equals 6.2 times 10 to the minus 10. Why not give it a try? We're going to assume that x is equal to 0 here. Once again, it's going to be this x we're going to get rid of. That's going to get us x squared, 0.01 equals 6.2 times 10 to the minus 10. Once again, we're going to multiply the bottom to the other side. After you do so, a little square root action on that. And if you do all that good stuff there, punch it in correctly, one of those things. Do a little bit of bang this calculator, that button, that. There we go. That's going to give you an x value here of 0.00000. I wish I knew scientific notation. 2.49 here. So here we're going to my first day. It's okay. We do need to check it, right? So we're going to divide it by what we're going to subtract that by. 0.01 times it by 100% here. Let's see here. Maybe times about 100, not 1,000. There we go. 0.02%. That's good news. That's a happy face all day. So that means that x value, if we go to our table, is going to be our H plus concentration. Dare I turn it into scientific notation and go with 2.5 times 10 to the minus 6 in this case? As I take a trip back to 200A, it'll be all right. So we don't want the pH, but it wasn't asked for. But obviously here, if we did calculate the pH, we should have an acidic pH. We actually do. It's like a pH here of 5.6, I think, in this case, if you did calculate it. Question on that there. Sometimes you just feel like writing zeros, you know, it happens. Any questions on that? Question on how to solve weak acids. Hopefully you can see it really is just like the equilibrium problems because frankly, it's an equilibrium problem. And the only additional thing you need to do basically in most cases is stick it into that pH equation. Questions? All right, so next thing we're going to talk about is actually percent ionization of an acid or even a base. And percent ionization, percent dissociation, however you want to word it, it's a fancy way of saying, you know, how much of the H plus came off of that acid. If we're talking about a base, it would be how much OH minus was released from that base. So that's basically what we're looking at. So to calculate the percent ionization of an acid, for example, you take the ionized acid concentration at equilibrium. That's a lot of words to say H plus, right? So they take the H plus concentration and they basically take the initial acid concentration, like we had there on the bottom there, And he times it by 100%. In case you're curious, that is the check we just did. Yeah, so that is actually the check that you do when you make the assumption, is you actually calculate that to see if it's 5% or less, which is reasonable. And what we see with a strong acid, as you can see here, it is 100% ionized, so it's just all going to break apart. Now, when we have a weak acid, we get some different percent ionization as you go through there. And as we talked about earlier, this is also why, as you can see, our assumptions may work in some cases and may not work in other cases. When you got a higher acid molarity, you have a smaller percent ionization. So the little bit that you lose is not a big deal in a sense. So it's usually going to be okay on that assumption. But again, if your acid concentrations over here, you have a much higher percent ionization. Again, back to the pizza example, might be because I want dinner and pizza, maybe. But if we have, again, only 2 pieces of pizza left at that point and you take one away, you just took 50% of what you started with. And that's obviously a much bigger proportion. If you had 12 slices and you took one away, you still got 11 to go, right? So a much smaller sort of dent on it. So concentration does play a big role in terms of the percent ionization, and also whether or not it's sort of significant, how much is the change that's going to occur. So if we look at a problem like this, we have a solution of formic acid that's 8 molar. It is 0.47% ionized. And in this particular case, we actually want to calculate what is the Ka value of our formic acid. So a couple of things that we know. First off, formic acid is a strong acid or a weak acid? It is a weak acid, and I know that because they're asking me to solve for the Ka value. So that's a pretty good hint that that is a weak acid. That also tells me that maybe I should roll like an ice table. It might help me through the journey here. So let's see if it does. We can write our equation. And again, it's just our formic acid breaking apart into H plus and a little HCOO minus, dare I say formate maybe. We're going to initially know that we have 8 molar of our formic acid. We have 0 this guy, 0 of that guy. Change would be minus x plus x plus x. Equilibrium would be 8 minus x, x, and x. So this is our normal sort of ice table that we would do here. We would also write our Ka expression in this case, which would be our products, our H plus, our formate, and our formic acid. And that equals, I don't know, because that's what we're trying to find in this case. So obviously at this point, we cannot put it into our equilibrium expression because we don't know what K is, and that's what we're trying to find. So we need to use some of the other information there to maybe help us. Well, we obviously use that. We do have one more piece of information, which is that this acid is 0.47% ionized. So if we use our percent ionization formula we just saw, which is the concentration of H plus over the initial concentration of your acid times 100%. I do know this. I do know the initial concentration. That would allow me to get to the H plus concentration. Why would that be important, say, in my ice table there? What is the H plus concentration equal at equilibrium? X. And that X is the same X as this one and the same X as that one. Very similar to what you did with the equilibrium experiment, right? So we could actually use the percent ionization to figure out how much H plus is there at equilibrium. And that will allow us to sort of back calculate our K value. So let's do that. That means we got 0.47% equals our H plus concentration over 8 molar, which was our initial concentration, times 100%. In this case, we're going to multiply the 8 to the other side and divide by 100. Yeah, so we're going to go this way. We're going to go multiply and divide. Yeah. So 0.47 times 8 divided by 100. gives us an H plus concentration of 0.0376 molar. That is the equilibrium concentration, basically, of H plus, which obviously, as we just talked about a second ago, that's going to be my X value. So at this point, I now pretty much have all these guys, and I could actually get the concentration of each of those. So our X here would be 0.0376 molar, or 0.0376 molar for that guy. And this guy would be 8 minus 0.0376 molar. And that's going to get me 7.9624 molar. I now have the equilibrium concentrations of everybody. Now I could go into this. So let's do that. That's going to get me basically that the Ka equals 0.0376 times 0.0376 divided by 7.9624. And that will get me I know. I'm going to clean it up like I took chemistry once. This is going to be 1.8, not so many zeros, times 10 to the minus 4. All right. See, I learned a little. That's good. Question on that. So you obviously can calculate just the percent ionization by plugging and chugging into the formula. Again, you could do it for an acid, which would be, like I said, how much H plus. You could also do it for a base. It would be how much OH minus that came out. You could also use it in the conjunction here to sort of back calculate some stuff. As we know, the H plus concentration at equilibrium is how much would be ionized, how much is left off when it reaches equilibrium, how much is freely floating around in that solution. Question.